Fagradalsfjall, 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 Fagradalsfjall.
Welcome to the April 2021 meeting in a very strange order tonight, because the main talk tonight was done at 6:30 on Zoom and we had about 15 there. The recording seems to have worked, so that's why I was late. I had to download it while I was so what is shown here is some of the things that have actually happened during the last month. First of all, we'll start with the International Space Station up there. That NASA has signed a deal for a reality TV show to be hosted on the International Space Station in 2023. They've already signed the deal.
Can you cut the ice landing?
Can I cut the ice landing?
What does that marry you now in space to do?
Turn the volume down. Yeah, so they've spent $55 million on it so far, and they've been given approval for NASA, so there'll be a group of people going up there. Now, I'm not sure whether it's a married at first sight up there or something a bit more heroic than that, given that the name of the company involved was Space Hero Partnerships, but that should be interesting. Then over on the right hand side, showing a laser firing into the air. Australia's signed up an agreement with Japan and the US to help remove orbiting space debris using laser technology. In this particular case, they're using the same technology as the professional observatories use for guide stars. So in other words, that compensate for the movement in the atmosphere. So they fire one laser to actually determine precisely what the atmosphere is doing at that instant, and then they follow it up with a more powerful laser along exactly the same path that's corrected for any distortions in the atmosphere, so that they're able to actually hit the target really accurately in space, or at least that's the theory. I don't think they've actually proven it in practice as yet. As you can imagine, other countries might be a little bit nervous about that sort of technology. Well, yeah, indeed. They might be rather unhappy. The one in the middle is that's twirling round and round, of course, is the Ingenuity helicopter on Mars. And hopefully many of you have saw that on the news on Monday night or Tuesday morning, and that was its pre-flight wiggle testing, I think they called it. It's where they tried the rotors out before shooting it upwards. And down the bottom is two images of Iceland. As you can see, capital Reykjavik shown there, before and after. So before on the left and after on the right, where you see that volcano erupting, and the pronunciation of that volcano is as follows. You'll be tested.
Fagradalsfjall, Fagradalsfjall,
Fagradalsfjall.
Fagradalsfjall.
Right, got that? Right, now this is a couple of minutes video that was provided by space.com about the Ingenuity helicopter taking off. This was after the actual live event. I'm not sure how many of you saw it. It was about 9 o'clock Australian's time. At that stage the video was very rudimentary. I think they only scraped a few frames from it, so you saw the thing suddenly lift off and then suddenly drop back down. But since that time they've managed to download more information. Shown here on the graph from the time going from left to right is the altimeter. So as you see, it's down to ground level around here. It shoots up to 3.19 metres, which only high as this roof, and then drops back down again. The distance between one tick mark and the other is 50 seconds. So as you can see, it was only in the air for maybe 40 odd seconds or so. Maybe I shouldn't say in the air, but it was above the surface for 40 odd seconds.
counter-revolving rotors are about flight, or is it about stopping the rotating motion?
Stopping it rotating, yeah. The same way as when astronauts use tools in space, they're also contra-rotating to stop the astronaut going the opposite direction to which the tool is rotating.
That's what I'm getting to do with the thin atmosphere too.
And also notice how sharp the rotors are on it, considering it's turning round at 2,500 RPM or whatever, to be photographed by the rover, without any blurring from 60 metres away is pretty good. Right, now the next one.
I heard they rotated.
Yes, Peter.
How did they get it out there into the open before they flew it up?
Well, it was actually mounted underneath the belly of the rover. So a pan dropped down from underneath, and it slid off, and then the rover drove away.
Okay.
And I had another image up there which I took off to put the video on instead, and it actually showed the track marks of the rover, so you could see where the rover had moved away from it, backed away. Now the next one is the volcano that occurred a couple of weeks ago in Iceland, and how do we pronounce that one again?
Same thing.
Yeah.
I heard the
That's yeah. Couple of things to note there. One, that's only 32 kilometres away from their capital city, which, as you could imagine, is less than even from here to Caulfield away, to have a volcano of that size. It's been dormant for 6,000 years, which is about the same time as the last active volcanic activity here in Victoria, and it just came from nowhere. They weren't expecting that one to erupt. So lovely volcano. So tonight, of sorts, Welcome to any new members. There were a couple on the talk a little bit earlier on Zoom, but obviously they're not here now. I'll go through the events past and coming. I won't actually go through the talk of Mike Cleeland because I've downloaded it successfully, but it's not been edited or checked through as yet. But it'll be up on YouTube in a couple of days when I finish splicing it all together. And if I was to show how it would go, it's fairly late now. Mark's given the sky for the month already, which is good. I'll show a short video on Ingenuity on Mars to give you a close look at it while it was still in the lab here on Earth. It was visited and looked at in some detail. Then walk through what is the origin of the Moon. So this is a bit of a geological flavour to it. What are the layers of the Earth and how do we know those are the layers beneath us, given that we don't have the technology to drill down that far. Then we'll look into astrobiology of caves and some of the laws that apply to outer space as well. So particularly with all these craft going up there. And then we'll close with another geological close with a bit of music to it as well. And this will show the last billion years of tectonic plate movement on the Earth. And this is the latest and the greatest. I think it was published only 2 months ago, and showing backwards in time. Now they actually showed it forwards in time. I've turned the video around so that you can try and see what happened to Australia as you go backwards in time. It's quite interesting. Okay, so recently what did we do? We had a viewing night for Strathcona girls down at Merritt, which went really well. And that was the one I think where we got the picture of the South Celestial Pole on the evening as well, thanks to Nerida. Then on the 21st of March we had the geological field trip down to Point Leo, which was very successful, very challenging sort of day, given that it was overcast and fairly warm, but threatening rain, and you really had to treat it as if you were going to get sunburned. We were at the maximum limit that we were allowed to have there by the authority that actually looks after Point Leo, because it's not looked after by the state government or local governments, it's an independent authority. And the original idea of it came from Sky Murphy, but about a year ago, but it was cancelled twice along the way because of COVID, and we finally got there on the third attempt, and by all accounts it was a fun and successful day. On the 31st of March, committee had a Zoom meeting where we finalised which meteorite we were going to buy, and I believe it's now arrived in Melbourne, although it hasn't actually turned up as yet. We discussed a bit about the fire inspection of the grounds here, that there were a couple of issues with that had to be addressed, and we talked about a further field trip as well. We'll see a bit about that in a moment. The 2nd of April public night was a talk given by Trevor, all about interstellar visitors, I think, from memory, with Uamalma, if I pronounce it right, and pretty good turnout considering COVID restrictions and people still quite nervous. Coming soon, well, we got the barbecue usually on the Saturday following this meeting. Then committee meeting about a week later, and we've got a couple of viewing nights coming up that we'll need help with telescopes on as well. St Augustine's primary down at Camp Mannion. Camp Mannion is close to where this field trip will be later in the year as well. There's a public stargazing night, the one on May, that Manfred will be giving the talk this time, and we all look forward to that. Then we've got a very large school, Parkdale Secondary, just under 200 Year 7 students, so we've been doing this for quite a while as part of their STEM program on the 18th of May. This year could be a little bit more challenging because we've lost a few regular members from that who've moved interstate. Next society meeting here on the 19th of May, and then a little further afield we've got a couple of school nights, one for Mount Erin Secondary in Frankston. I think this is probably the first time they've asked us along, and one of our newer speakers, Catherine, has offered to help me with that talk on that particular night to them. And the day after is the lunar eclipse, which will hold down at Frankston foreshore for the public, so there's no bookings involved with that. And the final point, much longer range, 21st of November is the date for the fossil trip to probably Sunnyside Beach in Mornington. And it'll be very, very similar thing to the Point Leo, except it's very, very different geology down there. So there are fossils there, and in fact a very famous fossil, as we heard actually on the talk tonight, was discovered down there by Tim Flannery, I think was said. Yeah. So as you see, we have Mike here. That picture was taken from Point Leo, Philip. So that's Mike holding one of the samples, I think, before we actually started walking along the beach. I think that one. Mike is a geologist. I think from memory, you graduated from Melbourne University, was it, in geology?
Yeah, I did geology at Melbourne Uni. That was a fair way ago. That was back in the Jurassic, sometime in the 70s. And yeah, things have moved on a good way since then.
And these days, Mike is an education officer at Bunurong Coast Education down at Inverloch. And given that he was sort of born and bred on Phillip Island and lives on Phillip Island, Inverloch is not far away. And you'd have to say it's probably a better commute than most people have each day, going to and from their jobs. I believe from the Point Leo field trip that we had, that he also has a fossil named after him as well, and we might find out about that as we go along, or I'll ask him when he comes back. But the Society went on this Point Leo field trip. We had about 50 people booked in for that, and a few people dropped out at the last moment due to one injury or another, actually sustained on the Saturday. And then other people quickly came in and took their spots as soon as they were available. So there was a bit of a waiting list of people to actually go on that field trip. We're actually quite lucky to get Mike, because he's off up to Queensland with his wife very shortly, to go up to a little place called Winton. And Winton in Queensland is quite famous dinosaur-wise, and they're going up there for the dinosaur digs, and I think they also help prepare the catering for it as well. So they're actively involved in a number of dinosaur digs around the place, and Winton is the next one that's coming up, and I think they'll be gone for a few months. And then the intention is to have something similar to the Point Leo field trip later on in this year, but it won't be to Point Leo. It will be to Sunnyside Beach in Mornington, and I think Mike actually has a slide that shows a bit of Sunnyside Beach in Mornington. It's an area where the Society has actually been to a number of times, or at least within a few hundred metres of there. It's close to somewhere called Camp Mannion, where a lot of viewing nights are done for schools. So Mike is dialing in via the 4G network, so via the telephone towers, and so consequently we're keeping our fingers crossed that we don't actually lose him. We seem to have he seems to have dropped off, and he'll be dialing back in a moment, I think, as well. Now, I believe Mike, who's speaking as well, also does a bit of stargazing himself, so there tends to be quite some overlap between the different disciplines of geology and astronomy and so forth, that people that do one seem to have interest in the others as well.
Yeah, that's right, Peter. I'm actually back. As part of the Easter holiday activities program that I run at the Bunurong Environment Centre at Inverloch, I had 2 astronomy nights down there, and both of them got rained out, unfortunately, but I just talked and talked and talked about. I have a bit of a presentation about the stars, but we have had some very good nights down there along the coast, where we go out and look over Bass Strait, and get a good look at the dark sky out there, see everything we have to offer. Anyway, will I get going with this presentation?
Yeah, I think so, Mike. Yeah. So if everyone keeps quiet, your screens won't flick up, but if they do, it'll go on to mute. So you'll notice, depending on what you're seeing on your screen, I'm only seeing whoever's actively talking at the time. So if I go mute and Mike starts talking, it'll flick over to him. And the idea of that is because this is being recorded and hopefully successfully recorded, it'll be able to be watched at a later time, and only takes up a little bit of space up in the top right hand corner showing whoever happens to be speaking at the time. So I've got control of the slides, but Mike, whenever you wish to change slides, just let me know and tell me, and I'll flick them over at this end. And I'll put myself on mute. I'll put myself on mute now, so I drop off, so no background noise causes me to come back up again.
All good. Okay. Yeah, welcome in, everyone. Good to be back with you. Some of the people I met at Point Leo. That was a pretty good day. We found a bit more than what we expected there. Anyway, so for those who I haven't met, I am the Education Officer at the Bunurong Environment Centre at Inverloch. I spent a fair bit of time at the dinosaur dig site. I have a background in geology, and I think I know enough to be dangerous about the geology of the Mornington Peninsula. So can we have a look at the next slide, Peter? There we go. Okay, so we start with a geological map of the peninsula, and it's actually rather complex. There's different rock type varieties in there. There's been a bit of earth movement. What we're going to do tonight is sort of look at examples of each of the different rock types represented there. The blue and the purple are both very old rocks from the Paleozoic. They're 300 or 400 million years old. The little bit of cherry-coloured rock on the lower left, Jaumann and Mount Eliza, is granite, which is about 360 million years old. The orange stuff on the lower right, Cape Schanck, Flinders, and extending over to Phillip Island there, is basalt, which is lava from volcanoes which have erupted in that area probably about 50 million years ago. So if you imagine before the sea level came up and disconnected the islands, it would have been a wide coverage of basalt from Phillip Island right across to the peninsula there. And then the light yellow across the rest of the area is more recent sediments, up to a few 100,000 or the last couple of million. So we've got a long time period represented there on the Mornington Peninsula. Okay, next one, Peter.
So on that one, Mike, does that mean in the gap there between the peninsula and Phillip Island that actually beneath the sea level it would also be orange as well?
Yeah, almost certainly. Don't think anybody's taken any samples out there, but the giveaway is that there are volcanic dikes, which are cracks in the rock through which lava has come up, and they occur on Phillip Island and on the peninsula. And in both places, they're oriented in the same direction. They both run sort of northwest, southeast. So that suggests that there's a connection between the volcanic rocks on the peninsula and those on Phillip Island. Yeah.
And I noticed on that diagram there's a lot of lines, fault lines on there as well.
Yeah, plenty of fault lines. Mornington Peninsula is defined by the fault lines, and I think we've got a better map coming up in one of the next slides, but you can see down the left-hand side of the Mornington Peninsula up against Port Phillip, we have a structure called the Selwyn Fault, and on the right-hand side, there's the Tyab Fault. And essentially what's happened, whoops, I've lost it. You're still reading me, Peter?
Yes, you're still there, Mike.
Oh, okay. Must be something wrong with my screen. Yeah, essentially what's happened is that the bays have sunk down a bit, and the Mornington Peninsula has stayed up at a high level. So there's been earth movements along those two fault lines, the Selwyn Fault on the left and the Tyab Fault on the right, such that the two bays are what we call sunk lands. So can we move on to the next slide where I think it actually shows that? Okay, that's got, yeah. Oh, all right, that's a closer look at the southern part of the peninsula, and that's a detail of the Selwyn Fault coming out there at Rowley Cove. And you can actually go down there and stand on the beach and look at the fault line where earthquakes have occurred. So essentially the left-hand side, anything to the left of the Selwyn Fault has dropped down, and everything to the right of the Selwyn Fault has stayed at a high level. Okay, can we have the next one, which shows it a bit better? There we go. Yeah, so they call these structures sunklands. So we have the Port Phillip sunkland and the Western Port sunkland. So they are areas which have sunk relative to the lands around them. So that kind of explains the surface topography. That explains why we have the peninsula and the Bass Hills to the east of Western Port standing up high, and the lower areas in the middle have sunk down. And then with recent sea level rise since the last Ice Age maximum about 18,000 years ago, sea level's been rising since then and has actually flooded out what were rivers flowing down through there and created Port Phillip and Western Port Bays. Okay, move on to the next one, can we, Peter? If people want to ask questions any time in this, please do, or put a question up on the, or comment on the chat digital box there. All right, let's start looking at some of the oldest rocks in the area, and this is one at the Mornington Quarry, where you see in the background some rocks which are quite steeply dipping. The layers are going down at an angle of about 70 degrees. And that's always a giveaway that it's pretty old rock, because it takes a lot of time for earth movements to move rock around in positions like that. So what we're looking at there is shale. It's probably about 400 million years old, and it's from the bottom of the sea. So that's telling us that this area would have been deep sea 400 million years ago, and there's ooze and mud slowly settling out at the bottom of the sea, and then the whole lot turns into mudstone and then turns into shale, which is preserved ooze essentially from the bottom of the sea. And then because of earth movements, it gets pushed together and angles get changed. It gets faulted and folded and turned into the rock we see today. So there's a bit of it exposed at Mornington Quarry. And I thought, last time I went to the Briars the other night, on the drive on the way in, there's a little quarry about half the size of a tennis court. And I just thought I glanced at it, and it might have been the same sort of rock in there as well. So there's a few outcrops of these on the peninsula. We have an incoming question from Therese. When did the last ice age begin and end? The answer is it's a bit complex, because when people talk about ice ages, ask them which ice age they're talking about, because there's been lots of them. Essentially, we are in an ice age now. We have been in an ice age for the last 35 million years, because that's essentially when ice started forming on Antarctica. Before about 35 million years ago, there was no ice on Antarctica. What's been happening since then is the carbon dioxide level in the atmosphere has been steadily dropping. So we've got ice forming over Antarctica. Just at the moment, we are in a interglacial, what we call an interglacial, where there's a temporary warm period. So some ice has melted and the sea level has risen up and filled up Port Phillip and Western Port. And that process has been happening over the last 18,000 years. But if things are left to their natural course of events, which probably won't be given the amount of carbon dioxide that's been emitted, but if things were left to their natural events over the next few thousand years, we would go back into our glacial period. And that process of alternation between glacial and interglacial is actually largely astronomically related. It's controlled by what we call the Milankovitch cycles, discovered by Professor Milankovitch. And what he found was, as the Earth goes around the sun, sometimes it rotates in closer to the sun and sometimes it rotates further out from the sun. He also found that the angle of, the angle of inclination on the Earth's axis actually alternates as well, between about 23 degrees and 28 degrees. So it's those cyclical factors which have a large role in determining whether we're in an ice age or out of an ice age. It gets a bit complex. I hope I haven't confused everybody by trying to explain something that's actually slightly outside my field. Anyway, Peter, will we move on to the next one? Which should be, okay, so that was a bit about the very oldest rock on the peninsula, the shale, which was from the bottom of the sea. The next thing that happened was, after that seabed sediment turned into hard rock, granite intruded, and granite comes up from underneath and solidifies. It comes up from underneath in liquid form at a temperature of about 700 degrees, And if it doesn't reach the surface and erupt as a volcano, it solidifies underground. And that's what happened there at Jaumann about 360, 380 million years ago. So that granite you're looking at there would have been under about 5 miles of other rock and has solidified there. And erosion since then has exposed the granite to the point where we can see it at the surface today. Makes you want to go for a swim there, doesn't it? That's a beautiful picture. I think it's one of the real estate agents trying to sell something. Okay, next slide, please, Peter. Okay, we're good to, there we go. Okay, so there's quite a bit of granite about. It's at Jaumann, it's at Mount Martha, and there we are looking into a quarry where granite was quarried there on the west coast of the peninsula for building stones and road gravel and those sort of purposes. I think you can still get into this quarry. I haven't actually been in there, but we have plenty of granite quarrying around the place. Here on Phillip Island, we have the Cape Willamai quarry. Okay, next one, Peter, which I think shows the view inside the quarry. Right, yeah, that's a close-up of the granite inside the quarry. So that's a good quarryable granite there. You can extract big blocks of it for building purposes. You break it open along the cracks, and I think that quarry is still in disuse. Is not in active use today, but it gives us a good opportunity to examine the surface of the rock. Okay, next one. Right, and that's a good one showing the formation of the granite. What was happening at the time this granite was being formed in that area was subduction. That is where a plate is going down underneath another plate. And in this situation, it looks like the bottom of the sea is going down underneath the east coast of Australia. And as a plate from the bottom of the sea slowly goes down, and this is going at a speed of a few centimetres a year, a couple of things happen. It gets closer to the centre of the Earth, so it gets hotter, and also friction between the two moving plates creates heat. So that's what causes the melting of the rock at depth. That might be 20, 30, 50 kilometres down. Rock starts to melt, and as you know from the meteorology, from the weather studies, hot air rises. And hot rock rises too, because it's less dense than the cool rock surrounding it. So this hot liquid rock material starts rising, and when it gets to that level there, just at the bottom of the green crust, and if it erupts at the surface, it forms a volcano, and if it solidifies at depth, it forms a lump of granite. So that explains our formation of granite. And then the removal of all that overhead material down to the level of the granite enables us to see what we see there at Jaumann and Mount Martha, the exposed batholiths of granite. Okay. Next one, Peter.
So Mike, in that one, is that the Pacific plate running underneath the eastern Australian side of the Australian plate?
Yes, I believe it is. And not only is that the reason why for the formation of all the granites in Victoria, and there's lots of them. There's Wilson's Prong, there's Mount Buffalo, Cape Willamai, and lots more. The Tynong, Pakenham out to the east side of Melbourne, Mount Kosciuszko. Yeah, there's this process has occurred right up the east coast of Australia. So essentially, I don't know whether it was the Pacific plate 360 million years ago or some other oceanic plate that was active at the time. But yeah, certainly something went underneath Australia and created a whole lot of granite intrusions, and also folded the rocks along the east coast of Australia. You might be familiar with synclines and anticlines. When you get this subduction process of plates bumping into each other, it folds the rock. It sort of concertinas the rock like the bonnet of a car in a head-on collision. So that's why when you're driving along the Eastern Freeway out to the east side of Melbourne, and you can see these big folds where the rock's going up and down, that's what's causing it. It's this subduction which causes both folding of rock and formation of granite like that. So
the granite itself, is that actually from the surface of the plate that is being subducted going downwards, or it was already deep under there and it's just waiting to become hot enough?
Interesting question. I think it's a mixture, and in fact, yeah, no, it's at least partly from the oceanic plate which is being subducted, because granite actually contains a quantity of water, and that water was originally seawater from the bottom of the sea. So we're getting seawater being dragged down underneath and mixed up with granite, which then rises to the surface and either solidifies there or erupts as a volcano. So that's one of the reasons why these volcanoes associated with underground sources of granite are actually quite explosive. It's because they've got a certain amount of water in the lava, and when that water reaches the surface, it turns to steam and erupts explosively. So that explains volcanoes like Mount St. Helens and Vesuvius and things like that. They are forming from this kind of lava, which has this tendency to blow its head off. So, yeah, I hope that partly answers the question, Peter. Any more, or will we move on to the next one? There we go. Okay, so that's dealt a bit with the two older kind of rocks, the seabed sediment, which has turned into shale, and the granite, which then intruded about 380 million years ago. We skip now to an event which occurred about 125 million years ago, where Australia decided to start to split from Antarctica. And as it split, a rift valley was created, something similar to the Great Rift Valley of Africa. When continents split apart, they create rift valleys. So this rift valley was creating, and as it was spreading apart, the bottom was falling out of it, and sediment was draining into it. And there at Sunnyside Beach, you can see some of the sediment which accumulated in this rift valley, which has turned to rock. And this is occurring at a time when dinosaurs were active across the surface of the Earth. They were not active at the time of the formation of the granite, that was too old. But at this time, at 125 million, that's why we have dinosaurs, dinosaur fossils in this rock. Now, I hope I'm not going to drop out here. I'm getting a sign saying my connection's unstable, so I'll keep going to the best of my ability. Next slide, Peter, is hopefully showing a little dinosaur bone that's been found there at Sunnyside Beach, and there it is. That could be the first fossil bone ever found in Port Phillip. It was found by Professor Tim Flannery just last year. I think he got lucky. There was last winter, and there'd been a bit of storm activity, and the waves had washed the sand off the rock and exposed this rock. And it's not a big area. It's only about the size of a tennis court. There's this little exposure of Cretaceous rock on the east coast of the bay, and Flannery knew it was there because he's a trained paleontologist. Before he started in his work in climate, Flannery did his PhD in paleontology. Anyway, so what he's found there is, we're not sure what it is. It's probably a small hollow limb bone going further into the rock, but at some stage that will be extracted out of the rock and hopefully identified, and we'll be able to say whether we've got the first dinosaur from Port Phillip Bay there at Sunnyside North.
So how large is that, Mike? Is that the size of a 20-cent coin? Or?
It is, yeah. I think we're looking at about 1.5 centimetre diameter. And it's going into the rock. We're looking at the outside wall there of a hollow bone. It's not quite circular. It's going off to the side there a bit. Can't say what sort of bone it is, but I wouldn't be surprised if that goes another 10 or 15 centimetres into the rock. But the process of that will be that we'll dig it out with a rock saw or an angle grinder or something and get it into the museum for preparation, and that involves grinding away all the rock from the outside of the bone to fully expose the bone, and then we'll be able to identify what it is. But at the moment, it's a mystery. It's probably dinosaur. It could be turtle or bird or mammal or any of the other things that we're getting around at the time. But knowing what we know from the dinosaur dig at Inverloch and Coonwarra and various other places, the kinds of bones that are found in fossils from that time in this rock are mostly dinosaur. Okay, well, we do the next one. Right, question is for us, is it difficult to obtain approval to extract fossil like this? Yes, it is. In that site, the approval would need to be gained from the local council or the foreshore. I don't even know who is in charge of the foreshore there. I suspect it's the local council. Where I work at the Inverloch dinosaur dig, if I want to dig out an exposed bone like that, I apply for a permit through national parks because it's part of the Bunurong Marine Park down there. So that's a formal process to go through, and usually it's not a problem because management authorities are interested in scientific research, and as long as one complies with safety conditions, it should be okay. Right, that's Atlas Copcosaurus, which is a little herbivorous dinosaur known from down near Cape Otway. So I wouldn't be surprised if that bone was from a dinosaur similar to that. That's about wallaby size, a couple of metres long from nose to tail. There you go. Okay, next one, Peter. We're getting up to the good stuff. We'll get into the volcanics. Oh, yeah, I thought we'd get into the volcanics soon. I went on a mineral collection trip to Cairns Bay once years ago. I think I actually saw a whale down there. We were sitting on the rocks at the end there, and there was a killer whale swimming past. That was a good one. Anyway, in the cliff there at Cairns Bay, you can see prominently layered structures. And how many layers are from the top of the cliff? I can see 1, 2, 3, 4, 5. At least 5 layers going down. Or is it 6? 1, 2, 3, 4, 5, 6, depending how you count them. Anyway, yeah, it varies from one place to the other. So what we're looking at there is lava flows. They are layers of basalt lava on top of each other, which have come out from a volcano somewhere and flowed out across the surface and solidified in position. There's probably another 4 or 5 on the scree slope at the lower part of the cliff as well. So we're looking at 10 or 11 lava flows on top of each other at that point, and there's probably more going down below sea level too. We have a cliff like that on Phillip Island at the Nobbies, straight across the channel there, where drilling records show that there's actually 43 layers of lava on top of each other going down to about 300 metres below sea level. And I don't know if that means there's 43 volcanoes have erupted once each, or 6 volcanoes erupted 7 times or something like that. But we know there has been repeated lava flows extending over that area. Let's have a look at the next one. Good. Again, Bushrangers Bay in the background. We can see how many lava flows there. 1, 2, 3, 4, probably 5. And a 6th one at sea level there. And just in the background below it to the left of that pool, the upper left, we see the columnar structure of the lava in that flow exposed there. And that's what we call organ pipes. You'll probably be familiar with Organ Pipes National Park out to the northwest of Melbourne, where you have a lava flow exposed there. And what happens is when basalt lava like this flows out of a volcano, if it flows over a flat surface, and if it has a flat top, then when it cools and shrinks, it cracks vertically. So that's what's happened there. We're getting vertical cooling cracks, which we call organ pipes, because they look a bit like the pipes in an organ. Okay, let's move on to the next one, Peter.
But if it was granite that was coming out from the eruption, it wouldn't form the organ pipes?
It wouldn't form basalt. Granite is geochemically different to basalt. If granite flows upwards and erupts at the surface, it produces a lava called rhyolite or andesite, or a couple of others. This lava is different. It has more iron and magnesium in it than granite, whereas granite has more potassium, aluminium, and silica in it. So it's different soup. Yeah, and what comes up from underground determines what erupts at the surface. So yeah, a bit of a different geochemistry going on here. For instance, in granite, you can find quite large crystals of quartz and mica. Well, basalt, you get 0 quartz. It has much lower silica content. Anyway, next one could be, Peter. Good. Yeah, Cape Shank's a good place for viewing basalt. Oh, there's good basalt columns in that rock on the in the distance there. You can see the up and down organ pipes exposed there. Difficult to see exactly how many layers of lava we've got on top of each other there, but I'm sure there's multiple. Let's have a look. I think the next one, Peter, is a close-up. Is that Pulpit Rock, what they call down there at Cape Shank? Oh, there it is. Yeah, that's good. Okay, you can see the up and down basalt columns in Pulpit Rock. So that's telling us that that is one lava flow. And I think the sort of reddish-brown layer underneath it is either a lava flow which has decomposed into clay, which they do, or it might be a layer of what we call tuff, which is solidified volcanic ash. What happens is when a volcano erupts, a whole lot of stuff goes flying up in the air, and then it falls down on the ground around the edge of the volcano and turns into this solidified ash deposit that we call tuff. So that stuff underneath the basalt lava is either the weathered top of the previous lava flow, or it's an ash fall, which has since turned into tuff. But that's quite a good exposure of the contrast between those two layers. Okay, next one. Anyway, the whole thing is telling us that it was quite an active area. This is not from the Mornington Peninsula. This is actually from Inverloch. But what we've got here is what we call a volcanic dike, where the rock has split open. In this case, sandstone has split open, and lava has come up through the split. So you're looking at a long, narrow crack about 1 metre wide, where here about 100 million years ago, lava was coming up the split. And we find quite a few of these on the peninsula, down around Cape Schanck and Flinders. So that is probably how a lot of the lava reached the surface. A lot of those lava flows that we saw in the previous pictures are probably coming up through these splits, through these volcanic dikes, which we can see still exposed. I'm sure I've seen them at Flinders and at Cairns Bay. Okay, let's have another look.
Do they actually form at the fault line? So is that the weak point that the lava would come up?
Yeah, well spotted, Peter. Yeah, this particular lava flow here at Inverloch is definitely on a fault line. You can see, well, not in this picture, but if you go further out, you can see that one side is displaced about 20 metres compared to the other side. So, yeah, the lava has definitely found a weakness and has pushed upwards and has pushed the rock apart and flowed upwards to the surface. At this time, the surface of the land would have been in this picture up about where the clouds are now. So we're looking at the lava that didn't make it to the surface, which solidified underground when the surface was much higher. So since then, there's been a lot of erosion, which has removed whatever lava erupted at the surface and has worn the landscape right down to this level. And landscape does change over time. If you assume there's an average erosion rate of the surface of the land we're standing on of about 1 millimetre a year, just rainfall washing soil downstream and out to sea. So there's 1 millimetre a year. That's 10 centimetre in 10 years, 1 metre in 100 years, 1 kilometre in 1,000 years. No, that's not right. 1 kilometre in 1 million years. So 1 million years ago, the surface of the land at that point could have been 1 kilometre higher. So we see big changes over long periods of time, just with gradual, slow erosion. Okay, let's see the next one, Peter. I think we're getting back onto the peninsula. All right, and that's what a fissure eruption looks like in full strength. So I think that's Iceland. So you've got the ground has split open and lava pouring out across the landscape. So I'm pretty confident that that's how a lot of the lava that the basalt solidified that we now see on the Mornington Peninsula got to be where it is. It's come up through dikes, through fissures like this, and spread out across the surface. So I don't think we would have had much in the way of classic cone-shaped stratovolcanoes like Fujiyama and Vesuvius and those sort of things. I'm pretty sure most of the volcanic activity would have looked like this. And this is probably about 50 million years ago. Okay, next one. I don't have any dates from the Mornington Peninsula, but I do have 2 dates from Phillip Island. There's the Nobbies was dated at 49 million, and the quarry at Coin Hill was 48 million. So I'm assuming that the Mornington Peninsula volcanics being connected to that are roughly the same age. Okay, now we skip to something much younger, which is Fossil Beach at Mornington. And I think this is only something like 1.2 million or 3 million or just a couple of million years old, because it's hardly even had time to turn into hard rock. It's still quite soft and clayey. Lots and lots of fossils have been exposed at Fossil Beach for many years. There was people picking fossils out of there when I was a kid and well before. Let's have a look at them now. I think we've got some fossils showing in the next slide. There we go. Yeah, huge variety of shells. So that's telling us that at this point, at that time, it was a shallow sea or a beach, and these are the kind of shells which were alive, these mollusks alive, and were turning into fossils at that time. Most of those are rather small. A couple of years ago, I met a lady who had collected a cowrie there, and the thing was about the size of a football. It was huge. I'm a bit foggy on regulations relating to fossil collection at that time. Obviously, there has been an awful lot of fossil collection from Fossil Beach at Mornington. Everybody's got a few in their bottom drawer in Frankston and Jaumann and those areas. But there are regulations about that, and I think they are explained on a sign at the car park at the place. All right, can we have a look at the next one, Peter? There we go. And moving on to some of the youngest rocks we're looking at, this is the Pleistocene. What we're looking at there, I think that's Diamond Bay. And Diamond Bay is composed of stuff we call calcarenite, which is essentially solidified sand dune material. It is back in the last ice age, or the last glacial maximum is the technical term, about 100,000 years ago. And southern Australia was quite cold and arid, and there was wind-blown sand moving across a whole lot of southern Australia. So what you're looking at there is wind-blown sand, which has set and turned into this stuff we call calcarenite. And there's some fossil and some good depositional structures, as well as some fossils preserved in that. And what you might be looking at on the upper right is a marsupial. No, I'm not sure it's that one. But let's have a look at the next one, Peter. That's it again. Okay. So what was found there is this skull, which is one of the giant wombats, otherwise known as Zygomaturus. And yeah, that was the place that it was found. But any chance we can go back to the previous slide and have a look at that? And yeah, that's it. There on the upper right, underneath that overhang, you can see a white patch, and that is those bones of that skull of that giant wombat. And I remember looking at it. I went there with a couple of museum people. And it's about 13 feet up in the air, and we were saying to ourselves, how on earth is anybody ever going to go up there, try and dig it out without the thing then falling down and landing on top? And what happened after a while was it fell down. A block of rock fell down and dislodged, and actually made it easier for the museum staff to collect that specimen. So that's in Melbourne Museum now. So can we move forward again? We'll see Dr. Tim Ziegler. That's Tim with the giant wombat skull, which was eventually exposed out of that rock. It turned out to be quite a good specimen of the skull, and the neck and the right shoulder was collected from that specimen. I think that's about 100,000 years old. It's Zygomaturus is the name, and it's one of the giant wombats. So let's have a look at that animal on the next slide. Diamond Bay has turned out to be a rather productive site. So there's been that find there. That's looking at the lower jawbone with the big teeth. And I'm also aware of a fossil emu shell. About a third of an emu shell was found there, and I think there's also some footprints from wallabies or kangaroos from the time. So that's in that Sorrento Diamond Bay area. And the good thing about that is the rock at that site actually erodes relatively quickly. It's quite soft rock. So you're always getting rock falls exposing new fossils, or erosion of the surface exposing things that have been buried underneath. Okay, next one, which I think shows what the animal itself would have looked like. There you go. That is Zygomaturus. So you see why they call it a giant wombat. It's a thing about the size of a rhinoceros. So that's what would have greeted the early arriving Aboriginal people coming into Australia from Southeast Asia. The latest date is about 65,000 years ago. There's stone tools in the Kimberley dated to 65,000. I think it'll actually go back to about 140,000, because I'm aware of research that was done in North Queensland in the Coral Sea, which shows that at about 140,000, there was a change in the type of pollen which was deposited in the Coral Sea between the Australian continent and the Barrier Reef. And what the pollen change showed was there was a change in Australia's vegetation from fire-prone vegetation to fire-resistant vegetation. So what that suggested was that at about 140 or 150,000 years ago, someone turned up in Australia and started lighting fires. So that's why I suspect that early Australian occupation might go back to about that time. Anyway, we definitely know that those giant wombats, Zygomaturus and the bigger one, Diprotodon, were there at that time. So it's quite possible that the early arriving first Australians might have fed on those. There's even a theory that they were tame. So when the first arriving Aboriginal people came over across the sea, they would have been starving by the time they got to northwestern Australia, and they've just walked up to these wombats who have never seen a human before. So you belt them over the head with a lump of 4B2 and start eating them. So that's the kind of thing that might have happened out there at that time. Okay, next one, Peter. What else have we got? Right, that's a closer look at the rock itself, and it has these prominent striations in them, and it's that alternation of the different angles. On the upper and top right there, you see layers dipping rather steeply. Underneath them, it's actually it looks a bit flatter, and that's actually typical of what we call aeolianite, which is fossilised sand dunes. So it's sand dunes which have been moving from right to left, and the sand keeps cascading over the front edge of the sand dune, and it forms that angled pattern. So whenever you see that at Sorrento, where else is it, Blairgowrie, Rye, Dramana, you can tell that you've had fossil sand dunes. And what's happened is I think that giant wombat has got caught in the soft sediment in the swale between two sand dunes and has fossilised there. Okay, next one. Yeah, there's another look at the layering pattern exposed in those fossil sand dunes. I think again that's Sorrento or Diamond Bay, forming these prominent layers in what's now relatively hard rock. The thing to look at in situations like that is footprints. If you get a flat layer exposed, it's possible to see footprints of the animals that were alive at that time about 100,000 years ago, and there's been some good discoveries of those down towards Wilson's Prom and out in Western Victoria. Okay, next one. And that's more fossilised sand dunes. Again, we see that sort of contrasting angled pattern. The interesting thing about this is that it's on Mars. That photo is not on Earth, it's on Mars. And it's layers of fossilised sand dunes, pretty much exactly the same as what we have on Earth. And that's how they form. So that's telling us a bit about planetary geology. I thought I'd throw that in tonight for interest of the Astronomical Society. So that doesn't surprise us. We know there is wind blowing on Mars. We know there's sand storms, there's dust storms. So this is telling us that in the past there has been active movement of sand dunes and formation of this stuff we call aeolianite. Okay, next one.
And does that mean that there's therefore been water?
Yeah, there's other formations which show there's been water. What we've got there is fossil sand dunes, which is shown that wind blows around. But the reason we know that there's been water on Mars is mostly the channels. There is sort of dendrite. When you look down on the surface from the satellite photos, you can actually see drainage channels where there must have been water or some kind of liquid flowing at some time in the past. So yeah, that's one reason why we know there was water on Mars. The other reason is that there still is. There's observations that there is frozen water ice on various places in Mars, mainly in the craters. It seems there's a couple of craters which are often in shadow, and there's water ice clearly exposed in some of those. So no doubt that there was and is water on Mars, which makes it easy for people travelling there. If travel plans to Mars and settlement of colonies there come to fruition, well, the good thing about that is you don't have to take tons of water from Earth to keep yourself alive. You can just melt the water on Mars and drink it. Okay, next one there, Peter. Right, is that it? We might have come to the end of the show. Okay, any questions? Or have we just about given everybody over information?
Yeah, I had one. I went to Fossil Beach a couple of weeks ago,
Right.
and had a look around down there. And a lot of it, there's heaps of clay. So is that just that it hasn't solidified yet?
Yeah, I'm pretty sure it just hasn't really solidified. It's not as though it's material which has turned to rock and then gone soft. I think it's just never really consolidated. So it's really just partly consolidated sediment. And that's why it's there's continuing to be lots of fossils exposed there, because the erosion rate is quite significant. Every high tide, it belts away and washes away some more clay and exposes some more fossils.
Russ has asked, what would be the most interesting mineral to be found on the peninsula?
Oh, good question. Yeah, there's probably good crystals of quartz to be found in the granites at Mount Martha and Jaumann. Don't think there's much in the way of gold. You know, even though you do have that Paleozoic sediment from the deep seabed that we saw in the first couple of slides at the Muller quarry. In other parts of Victoria, you have quartz veins coming up through that sediment in Ballarat and Bendigo. It's exactly the same rock, and you have quartz veins intruding into there, which are bringing up gold from deep down. What other minerals do we have? Oh yeah, at Point Leo, yeah, where we went there on the beach that day, it does have a history of collection of sapphires, rubies, and emeralds, I think. I know people have collected rubies and sapphires from there. Unfortunately, collection from that beach is banned now because there has been a fair bit of collection in the past. And the other good minerals to be found on the peninsula are in the basalt lava down on the southeast side of the peninsula, Flinders, Cairns Bay. That's what I was doing there the day I was there many years ago with the Mineralogical Society of Victoria. And what they were doing was collecting zeolite minerals. And zeolite, they're probably minerals you're not familiar with, but they form very nice microcrystal little minerals. And that's because they're growing in gas bubbles in the lava. What happens when the basalt lava erupts? It kind of comes out of the ground, and when it hits the surface, the pressure comes off and it starts bubbling. Just like when you take the bottle off a can of Coke or a cork out of a bottle of champagne, the pressure comes off and it starts fizzing and bubbling. Well, lava does the same. So when it reaches the surface, it starts this bubbling of release of gas such as water vapor and sulfur and carbon dioxide. And then when it cools and sets, some of these bubbles get stuck in it. So lava finishes up a bit like Swiss cheese with holes all through it. And then what happens is the various minerals start growing in the cavities, being brought in by groundwater, which is slowly soaking through the rock. So yeah, certainly down that Cairns Bay, Bushrangers Bay area, we do get quite a few of these interesting zeolite minerals in cavities in the lava, in these gas bubbles. And you can actually go to the mineral collection at Melbourne Museum and see quite attractive minerals on display there that have come from down there on the southeast peninsula. Okay, any other questions?
There's one question there from Philip asking, are there any truly ancient zircons on the peninsula?
Could be. Again, the ancient zircons, I would look in places like Point Leo, where we have these sapphires and rubies. Zircon might be associated with that, but I don't think we're going to get the genuinely ancient zircons like they do in northwestern Australia, which are 2 billion, 3 or 4 billion years old, because the rock's just not that old. The oldest rock on the Mornington Peninsula is that Ordovician shale around that Muller quarry there, and I'm pretty sure it's only about 400 million. So that's about the oldest zircon we get in that.
I believe from when we were at Point Leo, the most recent volcano in Victoria, I think, was stated as about 5,000 or 6,000 years ago. Yeah,
I've got an alternative theory. Yeah, the most recent volcano in Victoria was about that time. There's been a good, it was a really good, interesting story in one of the media outlets recently about how there's an Aboriginal story describing that. The Gunjat Mara people in the Western Victoria have a story that's been handed down about the being, the monster that was lying on its back and spitting its teeth into the sky. And that's thought to be a traditional story which has been handed down through generations of those people whose ancestors actually saw the eruption of one of those volcanoes in the Western District many thousands of years ago. So that's sort of officially regarded as the most recent volcanic eruption in Victoria. The alternative version is that in 1906 or 1912 or so. And again in about 1945, volcanic eruptions were observed off the coast of South Australia at a place called Beachport. Beachport is kind of on the coast not far from Mount Gambier, and the locals there reckon they saw ash erupting out of the sea in those two occasions. And it's never been confirmed whether it really was small eruptions of ash or whether it was discharges of gas from gas fields or something like that. But it's quite likely, you wouldn't rule it out because it is part of an active volcanic field. There are still hot rocks under there. And if we get future volcanic eruptions in Victoria, which we almost certainly will, it's probably going to be in that area.
So those volcanoes were what, more the traditional type of cone-shaped ones as opposed to these ones down here on the peninsula?
Yes, they are. Yeah, you can drive through the western district of Victoria and see plenty of these small cone-shaped volcanoes, Mount Elephant, Mount Noorat, Mount Gambier, Tower Hill, although that was more explosive. But yeah, that was the classic form of eruption where you had hotspot volcanism forcing its way up to the surface, where on the peninsula we had a different process happening. It's thought that the reason why you have a lot of those volcanic dikes on the peninsula where lava is coming up through these opening fissures is it's because Australia was travelling north and there was crustal tension. The tension of the surface of the crust was actually being pulled apart and cracks were opening up. So that makes it easier for the lava to come up through these pre-existing cracks and to reach the surface in fissure eruptions.
And,
okay. Yeah.
And are they likely to occur again?
Not on the peninsula. No. I don't think anybody's putting any money on volcanoes erupting on the peninsula. The last one there, probably about 50 million years ago, and when it's been extinct for that long, it's not likely to start up again anytime soon. That said, there's probably still a bit of hot rock underneath there somewhere, because I went to the hot springs. Where is it? At the hot baths at Jaumann. And that is supposedly coming from hot water from deep underground. But I don't think that's anything volcanic. I think it's probably coming from deep down up against the deep granite underneath that area, because granite has a certain amount of radioactivity, residual radioactivity. And as those radioactive materials continue to slowly decompose, they release heat. And so that contributes to heat at depth in those granitic sort of areas. So that's probably what's heating the water at those hot springs, but I don't think it's ever going to erupt anytime in our life.
Were there any last questions from anybody else here? Okay, well, given that, thank you very much, Mike, for taking the time to speak with us before you go off on your adventure up to Winton.
All right. Yeah, so I won't be seeing you guys for a while. In a month from now, I drive out of here for Queensland. My wife and I have got a job for 2 weeks. Well, she's the cook on a dinosaur dig up there out of Winton. So I'll be spending a fair bit of time washing pots and peeling spuds, and then we're going to spend the winter travelling around various sites of interest back there. So perhaps we'll get together later on in the year and have another visit to a site of geological or astronomical interest.
Absolutely. Well, thank you very much from all of us, and I'll close the meeting now. So bye, everyone. Those who wish to attend the rest of the meeting, it'll be at the Briars probably in about 3/4 of an hour, I think, by the time I get there.
All right, thanks, Peter. Thanks, everyone. Have a good night then.
Okay, bye, everyone.
For the month of April. So the highlights for April, I've tried to cut this down a little bit because a lot of it was probably not all that interesting to most people. The ones you really want to know are things like your first quarter moon occurring on the 20th of the 4th, so it's already occurred. And I put Mercury in ascending node there because I think last month we were talking about planets and their orbits passing through the ecliptic plane and being above or below. So with Mercury at its ascending node, it means for the next few months or however long it gets to the descending node, it'll actually be above the ecliptic plane. But if we were in the right position right now, we'd be getting a transit. So that's when the transits occur, when it's right between us. 2 meteor showers this month. We've got the Lyrids, which occur between April 14th and 30th, so they're active now. Most active night will be the 22nd, and on the 23rd you've got the Pie Puppets meteor shower, 15th to the 28th. The only problem is the moon might drown them out a little bit. And the Lyrids are a northern hemisphere meteor shower that does show some activity in the southern hemisphere. Full moon occurs on the 27th, so if you're looking for deep sky stuff, that's probably not the night to go looking. And the moon is also at perigee, which means it's at its closest approach to Earth, so the night later it'll be a supermoon as well. As for March, May, Uranus will be at conjunction on the 1st, which means it's in conjunction with the Sun. So if you have a hankering to look at a little green-blue dot, you're going to have to wait a little bit. Last quarter moon occurs on the 4th, and we've got a comet, Pons Winnicky, is actually approaching, so it's actually getting a little bit brighter as it goes. And it's in Aquila, and on the 7th of May, it'll be about 1 degree north of Eta Aquila, and at about 8th magnitude. So it's getting to the point it's actually quite visible in a model-sized telescope. New moon on the 12th and the 5th, which has certainly helped try and find that comet. They're not the brightest objects in the sky. And on the 12th and the 5th, Pons Winnicky will be 0.8 north of Theta Aquila, also about 8th magnitude. Seems to be a bit of a discrepancy in the book about it. Some are saying it'll be about 9th, others are saying 8th. So I'm going for the optimist option and calling it 8th. 12th of the 5th, moon will be at apogee, and on the 17th of the 5th, Mercury will be at its greatest elongation east, which means it's as far away from the sun in the evening sky as it's going to get. And a little bit more about that later on. And then on the 20th of the 5th, we've got the first quarter moon again. So those who were here last month, if you want to check your synodics and your sidereals and all that sort of stuff, you work out whether I was telling you a load of rubbish or some accurate text. Sky, don't look at the bottom, I know it says May. I've pressed the wrong chart. Okay, not all that different, it's just a little bit more that way, alright? So I'm sort of anticipating for next month. Some of the things up there worth having a look at the moment is Omega Centauri is up nice and high. It's a globular cluster for the newer members. Probably the best one in the sky, the brightest one in the sky, and certainly well worth a look. And a decent sized telescope, you can pick out all the individual stars. You've got the Eta Carina Nebula, which be a little bit difficult to pick out of there because that is in the Milky Way, the edge of our galaxy there, and there is a lot of stuff in that area. You've also got the Tarantula Nebula, and what I really like about the Tarantula Nebula, it's not even in our galaxy. It's actually in the Large Magellanic Cloud, so you're looking at a nebula that's in another galaxy. A fairly close one, but another galaxy. And down the bottom, you've got 47 Tucana, which is probably the second best globular nebula, globular cluster in the sky. Beauty is when Omega's low and difficult to see, 47 Tucana is usually high enough to pick out. Okay, and this is the sky looking to the north, that way. So if you stand and look out there, you'll notice it this way. You're starting to see Scorpio and Sagittarius popping up over here. Behind Sagittarius is the centre of our galaxy. Good luck seeing it. There's so much stuff between us and it that it's not really visible. And by stuff I mean space dust and all that kind of thing. You do have a few things to look at up in these areas. Once again, as I said, they're in the Milky Way, so they're trying to pick each individual one out could be half the fun. Down here, you'll see this little furry patch here. This is the Virgo cluster, and it's a Virgo supercluster of galaxies. All right, so it's got a decent telescope. It's a whole heap of galaxies in a very tight spot, and it is actually the part of the supercluster that we are a member of. I'll go back to this in a second. To actually find it, we're looking for Virgo and Leo. The way you can find those is Spica is quite bright, and Regulus. It's quite easy to find. So by finding those two, it's kind of a bit of a triangular position between those two there. And that's just a basic view of what it looks like. A lot of the objects there have got SEN numbers or NGC numbers. So if you type one into your controller, if you've got a go-to scope, you generally find a lot of them. These ones here, these roundy ones, these are irregular galaxies. You've got your spiral galaxies, an edge-on spiral there, another spiral there, and M88. Consists of about 1,300 member galaxies. Not sure what you have to do to sign up, I think it's got to be nearby. 65 million light years from Earth to the centre of it, and it's about 7.5 million light years across. So who can actually picture that? Not many. So it's also part of our address in the universe. We live on Earth, in the solar system, Milky Way galaxy, the local group in the Virgo supercluster. If an alien comes up to you and says, where do you live or where do you live? Tell him that, you'll know exactly where you are. All right. The planets, Mercury has moved through its superior conjunction on the 19th, so it's only just moved through it, so it's probably still too close to the Sun to view. And over the next, it's fairly speedy little planet, so probably over the next week or two it will actually start to move away as the sort of forward flexing gets back to elongation. So it is an evening object if you want to have a crack at looking at it, although it is fairly close to the ecliptic plane, so may not be too far above the horizon. Venus has just moved through its superior conjunction, but it's a little further from the Sun than what Mercury is, and so it'll take a little bit more to become visible in the evening sky, but it will become an evening object in the next month or so. Earth, not much happening with Earth this month. There's no equinoxes or anything. So I've sort of jumped a little bit ahead, give everyone a bit of a pre-warning. On the 26th and the 5th, so next month, there is a total eclipse of the moon. So basically the Earth passes between the moon and the Sun, casting its shadow on the moon. So I believe we are organising something, aren't we? So there will be something organised here. Lunar eclipse night, which is associated with the barbecue and the eclipse. So keep that one in your calendar, ready to go. Mars, as most of you aware, Mars is starting to disappear into the western evening sky, disappearing into twilight, moving through Gemini. On the 27th to the 4th, it skirts past M35, which is an open cluster in Gemini. Not too sure whether it'll be in the evening twilight, so you may not be able to see it. But for the astrophotographers, that might be one to have a little crack at. Jupiter, now a morning object. Jupiter's always bright. Whenever it's up, whether it's morning or night, it's always very easy to find. It's in Aquarius, in Capricorn, but moving to Aquarius. Saturn is still, it's also a morning object, still very close to Jupiter, or relatively close to Jupiter. In actual fact, I think the 4 gas planets are all in about the same part of the sky at the moment, with Uranus trailing a little bit. Uranus, low in the western evening horizon, but it's probably getting too close to the Sun now to start viewing it, given it's a fairly distant main object. And it moves into its conjunction in May. and Neptune will also return to the early morning sky in Aquarius after its conjunction with the Sun last month. So anyone wants to see a gas giant, that's early morning, set your alarm. Appearance of the planets. All right, Mercury passed through superior conjunction, essentially means it's on the other side of the Sun. I'll explain that a little bit later. And because of that, we do get to see the full face of it, if we can see it. So as it pops out from behind the Sun, you'll still see most of the face of it, pretty well all its face, but it's as far away from it as it can be. As it moves away, you start getting the shadow on the side that starts appearing as a crescent. Venus is behind the Sun, so you get a full face view if you can see through the Sun. So you can't really see it at the moment, but it's also fairly bright because of its relative proximity to Earth. And as I said, not visible. Mars disappearing into the western evening, so another 2 years before Mars will be back in our evening sky. But it will return later on in the year into the morning sky. Saturn and Jupiter always put on a good show. Saturn's still showing its rings tilted towards us. So if we look at Saturn through a telescope, we will actually see the rings quite clearly. Telescope. So Uranus and Neptune, one's a bluish green dot, the other's a blue dot. That's even through a reasonable sized telescope. The other stuff is Comet 7P Pons-Winnicky. Right at the moment now it's near Alpha Ophiuchus. So Ophiuchus is between Scorpio and Sagittarius, so it's a little bit on the horizon at the moment of the evening. It will move into the evening sky a little bit later in the month. And according to this part of the book, it's set to do from 10th to 9th magnitude, but the other part's at its 8th, so it's going to be 8th or 9th magnitude. Meteor showers, that's good. Alright, the Lyrans, as I said, they're a northern hemisphere shower, so they'll come from fairly low on the horizon, up the northeastern sky. And high puppets, southern shower, maximum activity around the 23rd, and they're cooperative one, they put on a good show between dusk and midnight. So you're out there, you can see some. Yes.
Can you see them with the naked eye?
Yes, they're a visual shower, so when you get the street, you'll see them. So if you're looking at the right spot at the right time. The pied puppets apparently are fairly slow moving meteors, tend to be quite large fireballs. So I think there was one actually the other day seen up in Surface Paradise. I'm not sure if it was a pied puppet, but anyone who looked on the internet would have seen that. That one up is photographed at Surface. Anyone see it? Take the word for it. Okay, so it was a fairly slow moving, quite a large fireball. So and they'll come from the puppets. And they do mention that we have to give us moon in the next week or so. So it's going to be fairly bright moon. It may affect visibility on it.
The only piece of observing equipment you need is a banana lounge.
Oh yeah, banana lounge, and you won't even need binoculars. Okay, on to practical astronomy. Tonight I'm going to talk about orbital aspects. Keep telling of these things with superior conjunction, opposition, and all that sort of stuff. So, particularly the newer members, I'll just go through what those various things mean. The reason it's nice to know the orbital aspect is you know whether an object's visible. You know, as soon as you know that Mercury and Venus are in superior conjunction, you know you've got no way of seeing. When you know that Mars, Uranus, Neptune, Saturn and Jupiter are in opposition, well, there's time to look at them. Is it worth looking at, and essentially where to look at for the object? So we have this little graphic here. In the centre there we have the Sun, and this orbit represents the inner planet's orbit, so either Mercury or Venus, and the Earth's orbit, and then out here is the outer planet's orbit. They only do the same think because the outer planets all act the same, we're just a bit vertically apart, bigger diameter. So with the Earth here, when Mercury or Venus is in this position, that's known as inferior conjunction. So they're between the Earth and the Sun. When they're on the other side, they're also in conjunction, but that's called their superior conjunction. So the two inner planets only have a conjunction, no opposition. All right, and I think I said Mercury is at its greatest elongation east. So that's this position here. This side of Earth is evening, midnight, and that's morning. So anything out here is a morning object. Anything out here is an evening object. Okay, so the way the planets move around, they actually move this way around. So when they disappear through superior conjunction, they will return as an evening object. Once they go through their inferior conjunction, they become a morning object. That make sense? Last month we were talking about the moon. The moon is between the sun and ourselves. It's a new moon. We're looking at the back of it, so we don't see anything. When it moves around to here, you've got your first quarter, your full moon, and your last quarter. Now, what happens on the 26th of next month is we would have a full moon. But the Earth's going to move between it and the sun, so you're on may not necessarily be on no, I don't want to tick that. So the Earth will move between them and will be on a line with the sun, so it'll cast a shadow on the moon. All right, and it's well worth seeing because you quite clearly see it's a blood moon, although photographing it picks it up a lot better. Now for the outer planets, when they're aligned with the sun, they're in conjunction. Fairly obviously, in conjunction with the sun. And when you're in that position, pretty obvious you're not going to be able to see them because they're the other side of the sun or they're up in daylight. And they all do that, but they're fairly slow moving compared to the Earth. So in actual fact, they don't move into conjunction. The Earth moves them into conjunction. You've got a planet here, and the Earth's here, it's in opposition, but as it comes around here, it speeds away from it. And then as we move to this position, put the sun between ourselves and that planet, it moves it into conjunction. Doesn't really matter, it's in conjunction with the sun, you can't see it. The other thing here is, the other side is it's in opposition. It's the opposite side of Earth where the sun is. Best time to view any of the outer planets. I think that's pretty obvious why. First of all, no sun interference with it out here, and secondly, it's as close to the Earth as it's going to get. All right? If it's out here, you're looking right across that amount of space. That's why Mars, if you watch each month, Mars gets smaller and smaller and smaller. The eastern and western quadrangle are basically when the outer planets form a 90-degree angle with the Earth and the Sun. All information tonight was provided by Astronomy 2021 and 3 available for those who would like your own copy of it. See Simon at the end of the night.
I'm at the Jet Propulsion Laboratory in Pasadena, and I'm here to see the first drone that's gonna fly on another planet. It's the Mars helicopter. Come on.
So this is our baby.
No way.
Yeah.
That thing right there is the actual machine that is going to take off and land on Mars. It's going with the Mars 2020 mission. That is the Mars helicopter.
This will be the first powered flight in another planet.
I mean, this is that. Now, it's necessary to say first powered flight because in 1985, the Soviet Vega missions deployed 2 helium balloons on Venus. They transmitted data for over 46 hours while floating at an altitude of 54 kilometers in Venus's dense atmosphere, which at the surface has a pressure of over 90 Earth atmospheres. In contrast, Mars has very little atmosphere, only around 1% of Earth's.
Flying this kind of a helicopter is equivalent to flying a similar helicopter on Earth at 100,000 feet. So you don't hear about many helicopters at 100,000. I think 40,000 feet is probably the record.
I checked. 40,000 feet is the record altitude reached by helicopters on Earth. 85,000 feet is the highest a plane has ever flown. On Mars, the air is even thinner than that.
Right, in terms of density is 1% of what you have in this room. So in this room, a cubic meter of air is about a kilogram.
Yeah.
The same cubic meter on Mars will be about 15 grams to 18 grams. So that
so you have to push a lot of air down.
Yes, you gotta get a lot of air flowing, and so the obvious trick, if you will, is to spin the blades faster.
It can spin between 2,300 RPM and 2,900 RPM.
That is fast.
That is fast, yes.
2,300. Here I'm trying to work out exactly how fast that is. So I looked it up, and on Earth, helicopters typically spin their rotors at around 500 RPM. So the Mars helicopter will have to spin its blades 5 times faster.
But there are some limits. We really don't want to get the tips of the blades breaking the speed of sound.
Because then you have shock waves and all.
And you get all kinds of funky aerodynamics and transonic flows and things like that. So you don't want to go there. So we, in our designs, keep the tip mark numbers down to below about 0.7.
So 70% the speed of sound.
Yeah, so it's very conservative.
One advantage of flying on Mars is that gravity is only 38% of what it is on Earth. Even so, making the craft lightweight was essential.
Keeping the mass of this vehicle contained during the entire design process has been the major challenge.
Every single part had to be considered. The entire vehicle is less than 1.8 kilograms.
Whoa.
So less than 4 pounds.
That's about the same as this laptop.
The blades are foam core with carbon fiber layup. Each of them is about 35 grams.
Wow.
Yes, it's quite light, yes.
35 grams is the mass of 6 quarters. Think about that. 2 35-gram blades lifting an 1,800-gram helicopter by spinning 40 times per second in just 1% of Earth's atmosphere. How long can it fly for?
It's designed to fly up to 90 seconds.
A minute and a half of flight.
Yes.
To me, that sounds like forever. When you're talking about another planet flying autonomously by itself in 1/100th Earth's atmosphere, I mean, come on. That's a long time.
It is, yeah.
One of the questions I had was, why didn't they use a quadcopter design? Well, because on Mars, the blades have to be so long that the whole craft would barely fit on the rover. 2 counter-rotating propellers provide the simplest design. They also generate lift more efficiently when stacked on top of each other.
The bottom rotor sees the more compactified flow. The top one pulls it, the bottom one sees sort of a more concentrated flow. Right. So the bottom rotor actually can do better than if they were separated apart.
But how do you test a helicopter designed for conditions on Mars on Earth? What would happen if you just took your Mars helicopter and you tried to take off on Earth?
It would just make a lot of noise.
Really?
And it probably wouldn't get to full head speed either.
Because of how much atmosphere we've got.
Exactly. It's like trying to swim in a thick soup. We have a really amazing chamber here on lab called the 25-foot space simulator. And in that chamber, you could simulate any kind of atmosphere you want. You can go to Martian pressures, you can stay at Earth pressures, whatever you want. But that only took care of half of the problem. That was the aerodynamics aspect of it. There's the other part, which is the gravity. We needed a way to fake Mars gravity here on Earth, and the best way that we could figure out to do that was a gravity offload.
Gravity offload just means pulling up on the helicopter, so it only has to support about 38% of its weight, just like it will have to do on Mars.
And effectively, it was a high-tech fishing reel. So taking a brushed DC motor, a reaction torque sensor, and a pulley, mounting that a couple stories in the air, and then attaching a fishing string to the top of the helicopter that would tug the necessary force required to offload the differences in gravity.
An actual fishing line?
Yeah, real fishing line.
But isn't that stretchy? Like, don't you want something that's perfectly rigid so as soon as you apply the torque, it gets applied to the craft?
Right. And we did a lot of testing with different vendors to find out which fishing line had the best spring constant for us.
What does the helicopter sound like? I imagined that in 1% of Earth's atmosphere, the helicopter would be pretty quiet.
Yeah, you're still at 1%, but it's still real loud.
Really?
Yeah, we have audio recordings of it too. But it's I would characterize it more like bah, something like that. When the gravity offload system was working and the chamber was pumped down, the helicopter thought it was on Mars. It felt like it was on Mars, the helicopter.
How do you actually steer this thing around and drive it?
So the way helicopters work is they have something called collective and cyclic. So what collectives do is they change the pitch on the blades uniformly. So throughout the entire revolution, if you move the collective, the blades will
change their
angle of attack, you'll get more lift. So that's basically what you would provide you heave control, right? You pitch more, you go up, pitch less, you come down. But then there's something called a cyclic on helicopters, which basically what it does is it modulates the pitch as it goes around. So it can pitch a little bit more here, less here. So it kind of like modulates. So what that does is it provides an asymmetric torque, right? When you're pitched up there, you get that additional torque. Now you get it, depending upon the stiffness of the system, you actually get it with that gyroscopic lag that can happen afterwards. So once you get an asymmetric torque, the vehicle wants to start pitching or rolling, right? So once it pitches and rolls, you're doing it stably, you are now pointed in a direction and your thrust vector now has a component that's horizontal in the direction that you pitched, right? So then you start translating in that direction.
I've heard that initially someone tried to fly it with a joystick?
Yes.
An early prototype?
If you were sitting right there on Mars and you were trying to joystick it, what is it like? And it's almost unflyable. And the reason for that, it's the aerodynamics of when you want to command a roll to the left, because you see yourself starting to move to the right and you start commanding a roll to the left, there's a delay aspect. So that delay effect makes it very, very difficult for a human to try and pilot it.
You can't fly this from Earth.
Because of the 20-minute kind of time delay, so you have to really send sequences.
So essentially, you're going to push a button and like 20 minutes later, it'll take off and do its thing, and then you'll find out.
The way this flies autonomously, it has onboard gyros, onboard accelerometers, and onboard camera, and altimeter, and an inclinometer. And so using that sensor suite, real-time measurement, against the terrain, and of course the gyros and the accelerometers sensing on board, the real-time estimation of the state of the vehicle is made continuously, again, hundreds of hertz, and then that's fed into the closed-loop control algorithm that takes the estimated state and then generates the correction that's needed at the blade level, and then the blades are continuously being controlled. So when you see video tapes of our successful flights, right, and the vehicle looks dead calm, is coming up and hovering and going laterally, coming back, the machines are working very, very fast and very, very hard. It just looks very calm, but yeah, so the blades are being continuously controlled.
That is amazing.
Yeah.
How will it handle a gentle breeze?
A lot of the movies depict
dust storms.
Dust storms as being very aggressive on Mars. The truth of the matter is that 1% Earth's atmosphere, there's very little matter actually hitting you.
I mean, you're using that to lift yourself.
Exactly.
So obviously,
so there's enough to lift, right? But we also need to spin at 2,200 RPMs to be in the ballpark of lifting ourselves.
We built our own wind tunnel that we put inside this 25-foot chamber. How many fans was it, Teddy? 960 computer fans. So, but it did sound like a jet engine taking off. So we built a fan wall array. It's called an open cross-section wind tunnel, where you don't need the walls. Just the fact of having an array of fans, we are very confident of it being able to go at 11 meters per second. Even this vehicle, if I had known that somewhere along the way I'd be building a wind tunnel to do this, I would have probably not taken the job on, right?
How long does it take to recharge?
We recharge the whole day. So the whole day at Mars.
Right.
So
but does that mean that you could do one flight a day kind of thing, in theory?
Yes, by design, it can.
What is the size of the battery?
Between 35 and 40 watt hours total.
That's equivalent to just 3 smartphone batteries. And get this, most of that energy isn't even used for flying.
It has to survive temperatures as low as about -80 to -100 degrees C at night. So we keep the batteries warm, and we surround the batteries with our electronics board, so the electronics boards also stay warm. we take approximately 2/3 of energy just keeping things warm and warming things up to operate. Only 1/3 of the energy is available for flight.
Do you have insulation on there to keep it warm?
Yes. When you look at the helicopter, right, you have the solar panel on top with the antenna, and then next is the rotor system, and then bottom, what you see, this cube, is what we call the fuselage. You are seeing it now actually uncovered because you're seeing the last day of final, we're recovering, for delivery to be integrated onto the rover. Okay, so usually you won't be seeing that. So the center of the cube is the ring of batteries, okay? There is space between the battery and the circuit boards that you're seeing, and then there will be a shell that we put on called the fuselage shell, and that will close like CO2, the gas around, and so the enclosure itself, we're using the CO2 gas as the insulation material.
Oh wow, no aerogel.
No aerogel. We did consider it was in the game. It was in the consideration in the beginning, and it turns out that just the CO2 as insulator itself was sufficient for us to close our thermal model.
Right.
And so, guess why we wouldn't want to use aerogel if we have a choice?
Wait.
There you go. You're welcome to our team.
Now, before the helicopter can experience the frigid conditions on Mars, first it has to get there. And that's a reminder that not only is this an aircraft, it's also a spacecraft.
It has to survive launch. It has to survive launch loads, which, easily exceed about 80 G. Because of the vibrational loads are 80 G.
Yeah. Then it has to survive the 7-month trip, complete with radiation. And finally, after pulling 9 Gs on entry into the Martian atmosphere, the helicopter needs to be deployed. This is going to be on the rover. Before you take off, does the rover pick you up and put you down somewhere?
We're going to be stowed underneath the rover on the belly pan on our side. And there's going to be several sequences of firings of explosive devices to actually rotate us right side up and then drop us on the surface.
For example, the very last thing that the rover does is it's got us by this bolt, it's holding us, about this high, and then it has to drop us, right?
Yeah.
So how do you undo a bolt on a spacecraft?
Just blow it up.
You blow it up. Basically, it's the materials, undergoes a phase transition, which certainly increases the stress in the metal part of the thing and makes the bolt break. It's called a frangi bolt.
Then once we're on the surface, the rover drives over us. It gets about 100 meters away, and then we have about a 2-hour counter internally where we'll wake up after 2 hours, wait to hear some RF transmissions, and if we do get that link with the rover, then great.
Our base station on the rover would issue the fly now command. First flight will probably be a mutual selfie, you would think. This is, after all, the selfie age. So
I like that as the goal of the first flight.
Yes, it is. In
Go
fact,
up,
the best time to fly this is at 11 o'clock in the morning local time on Mars. And the reason for that is we would have come out of the night where we would have spent a lot of battery power trying to stay warm. By 11 o'clock, the state of charge would have gotten to the point where we could fly without risking brownout on the battery and then dropping the whole craft to the ground. Also, 11 o'clock is where the sun would have warmed up things, so we don't quite have to heat up as much. And also, it's not late afternoon where, because of the warmth, the density has begun to drop, okay, and the winds have begun to pick up. Now, what we will investigate is after we get the first couple of flights under our belt, I'm sure we will try to fly in the afternoon and do more exploratory things. But the most conservative thing we can do is to sort of pick a mid-morning flight.
So what is the purpose of this mission? The Mars helicopter is first and foremost a technology demonstration to prove that we can fly on another planet. The helicopter can take color photos and videos, but its purpose is not to make scientific discoveries. Instead, it is to help engineers figure out how to design and build aircraft for future missions.
You can imagine something that's about 30 kilograms carrying, a 2-kilogram science payload, doing exploration, acting like a scout, like a small vehicle like this, scouting ahead for some future rover. Or it could be a gadget that goes and picks up some kind of samples and brings it back to a central lander for more sophisticated analysis. Or it could be a completely standalone craft, and maybe more than one, that are exploring places where humans and rovers can't get to easily. Some polar ice scarps, sides of cliffs and so forth. So the real emphasis here is to try to get back all the engineering data so that it can inform that future design.
Flying on other planets will provide a new dimension in space exploration. An aircraft is faster and capable of covering more ground than a rover, and it can provide higher resolution imagery than an orbiting spacecraft. So maybe one day aircraft will be the companions of future rovers or even astronauts exploring other worlds.
The planets formed in two ways. One way is that the heavier elements from the terrestrial planets, the rocky ones, and the gaseous ones have been formed by the lighter elements. So the rocky ones are heavier, they are closer to the sun, and the others are far away from the sun. Among the terrestrial planets, we have one planet with a large moon, that's the Earth. So the question is, why did only the Earth have a large moon? And so we can imagine four possible theories which explain the origin and the evolution of a moon in the Earth-Moon system. The first one is that the Earth captured another body, the moon, and forced it into an orbit around Earth. The problem here is we have samples from the moon, and we know that the material of the moon is very close to the material of the Earth's mantle. So it's unlikely that a body formed elsewhere in the solar system had the same composition as the Earth's mantle. The other theory is fission. So very fast rotating Earth can throw material out and this material can build a moon. However, we don't know that the Earth was rotating so fast at the beginning. And the second thing is we know that the moon is a little bit younger than the Earth. So if that happened simultaneously, the moon should be as old as the Earth. The third theory is very close to this. It tells that both bodies co-erected at the same time, and built out of the same material. There we have the problem that the distribution of the material is not completely the same. We know that most of the iron is in the Earth and the moon is depleted in iron, but has the concentration, the composition of the Earth's mantle. So co-accretion will not explain the depletion on iron. The fourth one is collision. So a large body collided with the Earth, destroyed the Earth's mantle, put material of the Earth's mantle and of the Earth's crust in the orbit of Earth, and there we built the moon. So this theory most likely solves all the problems. We have a similar composition from the Earth's moon and the Earth's mantle. We can explain the depletion in iron. We can put all the smaller problems we don't understand into the colliding body. And we know that this happened after the Earth formed, so the moon is younger. So in order to prove this, we really want to have samples not only from the surface of the moon, but also from the mantle of the moon. So the easiest way to get a sample of the mantle is to drill a hole. But the crust of the moon is about 40 kilometers at least. Though another possibility is to look at very large impacts, collisional impacts on the moon. And we know there are numbers of them on the moon, and we know this because we have mapped the moon starting from the Lunar Orbiter and Apollo missions. And in the meantime, we have a real good understanding of the geology of the moon due to the missions we have running, like Lunar Reconnaissance Orbiter, and we pretty clearly know that there is a large impact basin on the lunar far side. It's called South Pole Aitken Basin. It's large enough to destroy the lunar crust and to hit the mantle. So scientists are eager to get samples out of this impact basin. Each rock contains radioactive elements which will decay. If you melt a rock, you set the clock to 0 and you get the formation age of the melt. And having this, we really know when this basin formed, so we get more information about the age of the moon, and we also get material of the mantle because it's very deep. And these two informations are really needed in order to nail down the theory of the origin of the moon.
Much of our knowledge of Earth's insides comes from monitoring the thousands of earthquakes that occur every year. 5 centuries ago, the world had mostly accepted that the Earth was not only a sphere, but was thought to be of uniform rock throughout. 200 years later, Sir Isaac Newton, studying our planetary system, calculated that the interior of the Earth must be made of far denser material than the surface rock. Newton's estimate of the overall density of the Earth remains essentially unchanged today. In the early 1900s, scientists discovered they could use data from earthquakes as a method for looking deep beneath the surface. By understanding the travel times of different seismic waves to worldwide stations, scientists were able to calculate where boundaries occurred and what those boundaries represented. They thus determined that the Earth has 3 layers based on chemical composition: crust, mantle, and core. As an analogy for relative scale, these layers can be compared to an egg, with the shell representing the outermost brittle layer, the white the mantle, and the yolk the core. How did scientists figure out where these layers were? They used the arrival times of seismic waves to worldwide seismic stations. Seismic waves leave the hypocenter of an earthquake and travel in all directions. If the Earth had no change with depth, seismic waves would travel straight paths, but the Earth has composition, density, and temperature changes that cause the seismic rays to reflect and refract along boundaries as velocity in the mantle generally increases with depth. Innovations in computer technology, in concert with a steady beat of earthquakes, help scientists to continue to refine our understanding of Earth's interior. The basic layers of the Earth are grouped by their chemical composition. The crust is made of chiefly 8 major elements, shown here by their relative abundance: oxygen, silicon, aluminum, iron, calcium, sodium, potassium, and magnesium. At this scale, the crust is too thin to show as more than a thin line without zooming in. The crust ranges from 5 to 10 kilometers thick in the dense basaltic oceanic crust, and up to 75 kilometers in the thicker, less dense granitic rock of the continental crust. This difference in density and thickness of these 2 types of crust is the reason why the Earth has oceans and continents. The crust is often mistaken for the tectonic plates. However, the crust is just the top part of the tectonic plates. We'll return to the topic in a moment, but first back to the 3 layers. Below the crust is the mantle, composed of the same elements but in different proportion, with increasing amounts of the heavier elements in the rock. The chemical composition of the 2,900 kilometer thick mantle varies little from top to bottom, but there are distinct physical variations due to temperature and pressure differences. The uppermost mantle is relatively cool and brittle and ranges from 50 to 120 kilometers thick. Below this zone, the upper mantle becomes notably more plastic and malleable due to the right combination of heat and pressure. That ductile zone is known as the asthenosphere and varies up to 400 kilometers deep, depending mainly on temperature. The lower mantle comprises 55% of the planet by volume and is denser and hotter than the upper mantle. At the center of the Earth is the core, which is nearly twice as dense as the mantle because it's a metallic iron alloy rather than rock. Unlike the egg yolk analogy, Earth's core is made up of two distinct parts, the liquid outer core and a solid inner core. Although the inner core is hotter than the outer core, there's also greater pressure squeezing the atoms, changing the material from liquid to solid. The liquid outer core is convecting vigorously and generates Earth's magnetic field. But back to plate tectonics. As you recall, the cool uppermost part of the mantle is brittle. How can the top of the mantle be brittle when the same material in the asthenosphere is ductile? A big hunk candy bar can be used as an analogy. Like the uppermost cool mantle, when the big hunk is cold, it is brittle and breaks when bent. When you heat it up, it becomes ductile or plastic and can bend and flow. Earlier, we mentioned that the crust is merely the top of the tectonic plate. This uppermost brittle mantle behaves much like the overlying crust, and together they form a rigid layer of rock called the lithosphere that moves in unison. The lithosphere ranges from as much as 100 kilometers thick in the oceanic plate to 200 kilometers thick in the continental plates. It is in this brittle zone that earthquakes occur due to compression, extension, and shearing. Over billions of years, the cooled surface of the Earth has been broken up into the moving plates that are called lithospheric plates, or more commonly, tectonic plates. Because they are mostly more buoyant than the asthenosphere, they float above it. Convection currents, driven by temperature, pressure, and gravity, provide the mechanism for the process we know as plate tectonics. Earthquakes, volcanoes, and the Earth's magnetic field are all the consequence of the Earth trying to lose heat as it converts some of the thermal energy into mechanical energy in the process. Without the tremendous heat being released from the interior of the Earth, we would not have had the mechanism to drive plate tectonics. And without earthquakes, we may not have had a way to see so deep into the Earth.
My name is Penny Boston, and I'm an astrobiologist and cave scientist who focuses on geomicrobiology. I work in the United States, in the state of New Mexico, and I visit caves all over the world and look at the microorganisms that live there. I study what they do to the rocks and minerals and unique biosignatures that they may be producing because of those interactions with the minerals. So that's the setting that brings me to caves, and part of the reason that we are tremendously interested in the kinds of life forms that we find in the subsurface is for a number of different reasons. One is because they're very poorly studied here on Earth. There's very little work that has been done on these organisms, so it's an entire area of Earth biology that has only been studied a very little bit. So that's one major aspect of it. The second aspect of it is looking for environments that have different aspects of them that might be important models for life on other planets. So for example, on Earth we have hot caves, we have cold caves, we have acid caves, we have caves with poisonous gases in them. All of these different kinds of examples can inform us about how microbial life rises to the occasion and learns to adapt and live in these kind of environments. One of the other important aspects of caves and space exploration is that we now know that there are many caves on other bodies in the solar system, particularly Mars and Earth's moon. We have detected and mapped many of these features. And so the potential exists for future human use, for human exploration in these kinds of structures. The ability of the rock that is the overlying material over a cave is very good at helping to screen out very high energy ionizing radiation. And this is a major hazard in space flight. and space habitation on other planets. And so these natural features, because they already exist in these environments, provide us with an ability to actually modify those for human use with much less payload penalty than if we had to take all of that structure and all of that radiation protection with us. A very important aspect of being in the subsurface and using caves as an analog for extreme environments like other planetary surfaces is because it really is psychologically a transforming experience. When you go into the subsurface for a short trip into a show cave, for example, you don't really feel the full extent of it. But when you explore caves and you are in for many days, your whole sensory abilities are different. You don't hear the same things that you hear on the surface. You don't smell the same smells. You don't feel the wind on your skin in the same way. And so you don't see the same way because you're restricted to the light that you have with you. And so this really is like entering an alien world. It's like going on an expedition to another planet. And so for training people to experience that as a preparation for operations in extreme environments and outer space environments, it's an invaluable analog, and we have used that in many different contexts. And so I recommend it as an experience that all people who are aspiring to go into space or do other very difficult tasks would benefit from.
My name is Tia Flem-Detlefsen, and I work for the European Space Agency. Today I would like to tell you a bit about space law. Just like on Earth, we have laws in outer space that tells us what states are allowed to do. These laws were made at the United Nations Committee for the Peaceful Uses of Outer Space, and they were made to make sure that space was used for peaceful purposes and for the benefit of all humankind. The main treaty is called the Outer Space Treaty, and it says that everyone shall have access to use and explore outer space as long as they follow the rules in the Space Treaty and in international law in general. That means that states are not allowed to send up weapons of mass destruction into outer space, and they may also not harmfully contaminate another planet. The Astronaut Rescue and Return Agreement says that states shall render all possible assistance to an astronaut in distress. We also have a liability convention because, just like on Earth, if an accident occurs, we want to know who is liable for the damages. The liability convention tells us that if the accident occurs in outer space, we have to look at who is at fault. The registration convention says that states shall register their space objects. This way, we can have a better overview over the man-made activities in outer space. And finally, we had the Moon Agreement. It has some principles about how we should conduct our activities in outer space. However, one of the concepts is a bit controversial, called the common heritage of mankind, about how we should manage and own the moon. Therefore, no spacefaring nation has ratified this agreement. Have you ever watched a clip of the first moon landing, where Neil Armstrong and Buzz Aldrin planted the American flag on the moon? Maybe you thought about what this meant, because back in the day when you planted a flag, it indicated that this new territory was yours. However, no one owns outer space, so planting your flag there won't have this effect. That's because Article 2 of the Outer Space Treaty says that outer space is not subject to national appropriation by sovereignty, by means of use or occupation, or by any other means. Article 1 says that outer space is the province of all mankind. So, if you go to outer space, you're not allowed to bring back your own souvenir because space belongs to all of us. Astronauts are also not allowed to own their own space souvenir. But what other laws would apply if we imagine that they live in an international moon base? If we imagine that the moon base consists of different modules and that each member state have their own module, then it would be the national law of that member state where, for example, a criminal activity is conducted that would apply on board that module. Now, if we compare the International Moon Base to the International Space Station, then we can imagine that member states would like to make a similar intergovernmental agreement where they agree on how they shall conduct their activities on board, and it would include principles such as peaceful uses and international collaboration. Now, when the astronauts go outside of the moon base and onto the lunar soil, it will be the same space treaties that I was talking about earlier that would apply. That means that if an astronaut wants to conduct a scientific experiment, they have to make sure that they do not interfere with the activities of other astronauts, both current and in the future. It also means that if a criminal activity occurs outside the base, then it would be international criminal law that we also know from Earth that would apply. When we go somewhere new, and we have to build a new base, then the easiest way is to use the materials that is already there instead of having to bring everything with you from home. This is especially true when we're talking about distances to the moon. Here we can use space resources such as dust and rocks to use as construction. And if you would like to know more about this, then you can check out the ESA educational video on space resources. Now, for the legal side of it, what we're looking at is how to regulate it so that all states have a fair and equal access to space resources, and that it's done in a sustainable way.
Right, so now to close, we look at the plate tectonics of Earth for the past billion years. And a picture there of Antarctica shows you north is in all directions other than the south in the middle. You haven't realised that already. Now, before I start the animation, notice where Australia is. That's showing not only the bit that's above the water, but also the continental plate below the water. So keep your eye on where Australia is. Watch how it wanders around the Earth. And right at the very top in the centre, where it currently says 0 mega annum, so in other words that means 0 million years, watch that counter. So when it gets to 65, that's when the dinosaurs disappeared. Alright, so keep watching it going backwards. These other boundaries are the various larger plates around the world, and this is being worked out several techniques, and this is the best available knowledge. where's Australia? If you actually kept an eye on it, it went right up into the northern hemisphere, even further north than even where Scotland is today during that period of time.
No, using our crawling up stuff. From what I can see.
So they worked that out by various methods. Obviously comparing, to start with, comparing the shapes. So everyone's heard about cutting out the shapes of the countries and being able to slot them together like a big jigsaw puzzle. That's all right in short periods of time, but when you go back to the movement of the tectonic plates over time, it's a different matter of looking for where are the similar rocks found on other continents. So in other words, you try to match individual areas, but even that doesn't work when you go back more than about 400 or 500 million years. Then there are other techniques, chemical techniques that are used going further back than that. So that's the level of knowledge going back 1 billion years. Earth is only 4.5 billion years old, 4 billion years since the moon was ripped out of us. And 1 billion years is the furthest back that they've been able to work it out so far.
And that's also folding in on itself as well.
Indeed, yeah.
And at a great speed, the same speed as their fingernails grow.
Yes, exactly. Okay, and with that, I will call a close to this very unusual meeting this month, and we'll see you here in May. Thank you very much.